In this video, I want to walk through some concepts behind the Malonic Ester synthesis. You'll see that knowing this really helps you to understand the acetoacetic ester synthesis a little bit later also. So we'll talk about what this achieves, how it achieves it in terms of the mechanism, and a couple things you can use to remember it. Okay, so first, what does it do? The general idea summarized behind the Malonic Ester synthesis is written here. Now, some languages, like English or French, you read left to right. Other languages, like Arabic or Hebrew, you read right to left. Chemistry is a language that you can read in both directions. One sentence will give you two statements, depending on how you read it. If you read this left to right, then you would see an alkyl halide. And what this statement is telling you is that if you have an alkyl halide, then you can make a carboxylic acid. Now, you would add two carbons in the process, but you can make a carboxylic acid out of any alkyl halide using the Malonic Ester synthesis. That's one statement that you can get out of this chemical sentence. Another statement you can get, if you read it in the reverse way, is if you want to make a carboxylic acid, whatever the carboxylic acid may be, all you need is an alkyl halide. If you want to make a carboxylic acid, you could make it from an alkyl halide using the Malonic Ester synthesis. So you sort of keep your eye out for two things. One thing is an alkyl halide, and now you want to connect that to being able to create a carboxylic acid out of it. And the other thing is, anytime you see a carboxylic acid, think, I could make that from an alkyl halide. And the way that you create this transformation is through the Malonic Ester synthesis. So let's see what that involves. Every time you do a Malonic Ester synthesis, you will use these reagents. You will always start with this molecule on the left, and that is called Diethyl Melanate. We'll talk a little bit more about that in a second. You will always start with diethyl melanate. You will always add sodium hydroxide and ethanol as the first step, always. In the second step, you'll always add an alkyl halide, and the alkyl group will depend on what alkyl chain you want on your carboxylic acid in the end. Those are your first steps, and then when you're finally done, your last step will always be add hydronium, so aqueous acid, and heat. And you will always get this carboxylic acid and these two carbons adding on there. And as we draw the mechanism, you'll see that these two carbons in the carboxylic acid is ultimately coming from half of this diethyl melanate molecule. But before we get into the mechanism, let's take a second to talk about what this molecule is, since it's going to be in every single one of these Malonic Ester syntheses. The name is a little strange, and it's coming from names for dicarboxylic acids. There are names, if you go from the smallest to the largest, dicarboxylic acids, there are common names for these. And these are useful to remember, not necessarily for our class. You wouldn't have to memorize any of these for a test that I will give you in this class, but they're useful to know in biochemistry because they're used in a lot of processes, in biochemical processes, in different steps of metabolisms. So they're useful to know. What I've arranged here are different carbon chains, starting with 2 carbons, 3, 4, 5, 6, and 7, so just going in order. And what you can do is have dicarboxylic acids. Carboxylic acids always occur at the ends of these chains. So you could have a dicarboxylic acid has a carboxylic acid on both ends of the chain. The smallest one is called oxalic acid. It's in the leaves and the stems of rhubarb. The concentration is much larger in the leaves, which is why you would never eat the leaves of rhubarb. At higher concentrations, oxalic acid makes you hallucinate and then eventually die. If you have a 3-carbon chain and you create a dicarboxylic acid out of that, then you have something called malonic acid, and you should see what this is suggestive of. We're talking about the Malonic Ester synthesis. So we'll get back to that in a second. If you had 4 carbons and you create a carboxylic acid, then you have what's called succinic acid. If you have 5 carbons and you turn that into a carboxylic acid, a dicarboxylic acid, then you have something called glutaric acid. 6 carbons, you turn that carbon chain into a dicarboxylic acid, you'll have a molecule called adipic acid, appears a lot in biochemistry, and then if you have 7 carbons and you turn that into a dicarboxylic acid, you'll have something called pimelic acid. Now it's easy enough to draw these structures because you're just starting with 2 carbons and just adding an extra carbon, and you still have the 2 carboxylic acids on the end. What might be tricky is to remember these names, and so while I'm with you, while I have this time with you, I'll show you a little mnemonic device that might help with that. So you'll notice here, you have, if you just look at the first letters, we have O, M, S, G, A, P. And there's a mnemonic device, popular mnemonic device that you can use. It's so O, M, S, G, A, P. It is, oh my, such good apple pie. Oh my, such good apple pie, and that will help you remember oxalic acid, malonic acid, succinic acid, glutaric acid, adipic acid, and pimelic acid are the smallest of the dicarboxylic acids. So I wanted to show that to you because hopefully it'll be useful to you in the future in biochemistry, for example. But what's useful for us right now is this malonic acid. Notice that it is the second one. It's the my in oh my. So oxalic acid is the smallest, that's the O. Malonic acid is the second. It has 3 carbons and carboxylic acid on the end. So that's malonic acid. But if we take malonic acid, and here, I'll just flip this over. If we take malonic acid and we change this leaving group into an ester, these leaving groups into esters, well, now we would name this as an ester. These carbon chains that don't have the carbonyls are named as branches. We have 2 of them, so diethyl. And the backbone was malonic acid. When you change that to an ester, you get rid of the ic acid and you fill it in with 8. So diethyl melanate, that's where this name is coming from. So because this plays such a crucial role in this reaction, I wanted to walk through the derivative of that name with you. So hopefully it'll be easier to remember the structure for that now that you have that. And knowing the structure for diethyl melanate will help you, as I said, remember the structure of another molecule we're going to use in the next reaction, the acetoacetic ester synthesis. Okay, so anytime you do this, you always start with diethyl melanate. This will always be the sort of recipe that you use here. So let's go step by step, see how this works. In the first step, you take diethyl melanate, and what's special about this is you have a carbon in between, this alpha carbon. This alpha carbon is alpha to both of the carbonyls, to 2 carbonyls. And so the hydrogens on that carbon, on that alpha carbon, will be very acidic. And there are 2 of them there. We're just going to deal with 1 at first. But remember that there are 2. Okay, so I'm just going to draw 1 in. We'll see how it works with 1. And we'll apply that to the second one if we need to. In this first exercise, we use always sodium ethoxide. And the reason for this is similar to why you would use sodium ethoxide in the Claisen condensation. You want to use ethoxide because it's not just a strong base, it's also a strong nucleophile. And so while it will act as the base, as we'll see in a second, it could also act as a nucleophile, attack the carbonyl, you get the tetrahedral intermediate, snaps back down, and you could have this nucleophile replace the leaving group of the ester. So long as the group, the base, matches the ethoxy or the alkoxy group in the ester, that side reaction won't change your original molecule. So you want that ethoxy group to match you want your base to match the ether of the ester. You want it to be an ethyl group to match the diethyl groups in diethyl melanate. So that side reaction, that nucleophilic acyl substitution doesn't matter, doesn't change anything. So if that side reaction doesn't matter, what does matter is this is a base and can steal this very vulnerable alpha hydrogen. The electrons can snap back onto the alpha carbon. And so we do a proton transfer. So now we have this lone pair on that alpha carbon. And that can act as a nucleophile. Sort of like we saw when we were alkylating the alpha position, we can sort of alkylate this alpha position. We can treat this nucleophile, this carbon nucleophile, with an alkyl halide, just like we saw in the previous couple of videos. And so that's what this second step is all about. So whatever alkyl halide you have, and keep in mind that this R group is any carbon chain, although because this is going to be an SN2 reaction, you'll want that to be either primary or secondary, not tertiary. And remember that this capital X is any halogen, so chlorine, bromine, or iodine. And the halogen is slightly electronegative, pulls electrons to itself. The carbon that it's bonded to will be losing those, becomes slightly positive. So this nucleophile can go and attack that carbon and kick the leaving group off. So standard SN2 reaction, we have nucleophilic attack happening at the same time as loss of a leaving group. So what we get after that SN2 reaction is we have our original diethyl melanate, but instead of two hydrogens, one of the hydrogens has been replaced with whatever the R group was in your alkyl halide. Okay, so that is the second step. So first step turns the alpha carbon into a nucleophile. Second step takes that nucleophile and does an SN2 reaction, and this alkyl chain gets added. And the halogen leaves as a leaving group. So now we have this third step, hydronium and heat. First, let's think about what happens with hydronium. When you add acid, or when you add aqueous acid, like hydronium, that will hydrolyze these esters. You might remember you drew that mechanism on a previous test, the acid-catalyzed hydrolysis of an ester. That mechanism is rather long, and so to make this video more manageable, I'm not going to draw that mechanism out right now, but I will tell you where to find that mechanism drawn. That will be in a video in the carboxylic acid chapter, and the title of the video will be Acid-Catalyzed Hydrolysis of an Ester. And we showed it, for example, when we were showing how triglycerides break apart. So it's really just nucleophilic acyl substitution, but with a whole bunch of proton transfers. And what you get at the end of that is hydroxides replacing your ethoxides or alkoxides of the esters. We still have our R group there. Okay, well now you can start to see those two carbons with the carboxylic acid that are going to add onto your R group. Remember that was sort of what we noticed was adding here, those two carbons and the carboxylic acid onto the R group. And they're coming from these two carbons and the ester, one of the esters in diethyl melanate. Okay, so we have this. Now this is where things get a little weird. I'm going to redraw this carboxylic acid. This is where the heat is important. I'm going to redraw, well, actually, I'll redraw this carboxylic acid like so. So I'm just going to twist this single bond a little bit, rotate it, so that you can see an interaction that happens. So what happens now is a pericyclic reaction. The oxygen in this first carbonyl is slightly negative. So let's actually draw in these charges. The oxygens are slightly negative, and the stuff that they're bonded to is all slightly positive. Okay, so the slightly negative oxygen wants to stick to the slightly positive hydrogen there. But if it does that, where will these electrons go? Well, the most attractive place nearby is this slightly positive carbon, so they swoop down to create a pi bond in that direction. But then something has to leave. These electrons here get pushed away. Where are they going to go? They're attracted to the slightly positive carbonyl over on the other side. And, oops, I drew this, but it's really these pi electrons that do this. And so you have this pericyclic reaction where everything's happening in a ring. This is a 1,5 sigmatropic rearrangement, if you want to think of it that way. But you have all these things moving at the same time. Okay, let's change each of these things one at a time. I'm going to keep this up here as a reference, and I'm going to redraw each of these arrows one at a time. So this pi bond won't be there anymore. It instead will be a bond to this hydrogen. The bond to the hydrogen won't be there anymore. It instead will be a pi bond to that oxygen. The sigma bond here, won't be there anymore. Oops. Instead, it will be a pi bond to this other carbon. Okay, now everything has kind of a weird shape here, but notice sort of one of these things that has happened. This is carbon dioxide. Oops. This is carbon dioxide. If you take this here, you have this carbon in the middle that's double bonded to oxygen on two sides. So this is carbon dioxide. That bubbles away. So notice this carboxylic acid got turned into carbon dioxide. That bubbles away. And we've seen the intimate connection between carboxylic acids and carbon dioxide before. We've seen how you can take, for example, a Grignard reagent, and it would attack the carbon in carbon dioxide and create a carboxylic acid. Well, now we're seeing how that process can come undone. You can have a carboxylic acid and it can break apart and bubble away as carbon dioxide. The other piece of the molecule that we have, this over here, let me redraw that. This is a type of enol. So you have this carbon here. So you have an alkene and an alcohol, that's an enol, and that undergoes keto-enol tautomerism. You might remember from the very beginning of this chapter, and you also would have been introduced to it in the alkyne chapter of Organic Chemistry 1 when you talked about acid-catalyzed hydration and hydroboration oxidation of alkynes. You would have been introduced to this concept of keto-enol tautomerism, and we talked about it earlier in this chapter too. Whenever you have an enol, it mostly reconverts, tautomerizes into a ketone. And so here, and if that doesn't seem familiar, I encourage you to watch the first 3 or 4 videos in this chapter. And so you end up with those 2 carbons and the carboxylic acid at the end of that chain. Oops. Okay, so ultimately that's the change we made. And so every time you do this malonic ester synthesis, you'll start with diethyl melanate. You will always use sodium ethoxide in ethanol. The ethanol is just serving as the solvent here, because if this base steals the hydrogen from it, it just reproduces another ethoxide. Once that turns this alpha carbon into a nucleophile, once you have that nucleophile, you can do an SN2 reaction. That puts the R group there. This hydrolyzes the ester, turns it into a dicarboxylic acid, and heat decarboxylates it. Decarboxylation is also a really interesting biologically significant reaction, and it can happen in some plants, even including if you do research, for example, the companies that are working in Colorado for the marijuana industry work with decarboxylating a cannabinoid in order to convert that into a different product for their businesses. So decarboxylation is relevant from a biological standpoint too. There's one last thing I want to point out. Aside from the fact that here we're taking an alkyl halide and turning it in, adding 2 carbons and turning it into creating a carboxylic acid. And that is that diethyl melanate has 2 hydrogens. And they're both acidic. They're both alpha to both of those carbonyls. So if you wanted to, you could take these first 2 steps and double them. Now they would become steps 3 and 4. And then this would become step 5. You always do this acid and heat at the end. But what would happen here is this first base would steal the first one, turn that into a nucleophile, and you'd react it with an alkyl halide. And then you could do the whole process over again. The second base would steal the second alpha hydrogen, turn that alpha carbon into a nucleophile again, and do another SN2 reaction. So you can really add 2 different carbon chains onto there. And they don't have to be the same. They could be completely different carbon chains that you add onto that alpha carbon to create a carboxylic acid. And to do that, you just repeat these first 2 steps once for each of the carbon chains you want to add. Okay, so hopefully this video gave you a greater understanding of how this malonic ester synthesis will work in terms of the mechanism, what each of these pieces are doing, and why they're there. In the future exercises, we're going to apply this knowledge to synthesis exercises, where I won't go over all these details again, but I will assume that you understand them from this video.